So what the fuck? I'm not sure.
Deep-sea operations can be more challenging than space exploration. When astronauts sent messages from the Moon, there was a 1.2-second delay before they were heard on Earth. Yet when aquanauts sent signals from the Challenger Deep, they took 7 seconds to be received. Only the most advanced technologies can help us explore this complex frontier. Underwater inspection and monitoring are essential for many industries. Operators deploy professional divers and ROVs, but their effectiveness is limited, especially at great depths or in rough seas. As maritime operations expand into deeper waters, more remote locations, or more complex conditions, operators need more intelligent, safer, more cost-effective solutions. Autonomous underwater vehicles, or AUVs, are wireless robots that can safely perform complex tasks, potentially at lower costs than divers and ROVs.
The goal of Kraken was to develop innovations that are not there today. If we can develop products that are bigger and better than what's out in the market today, we will be able to compete. We are a marine technology company focused on the design and development of underwater sensors and vehicles. Ocean Vision, which turned out to be the very first project approved by the Ocean Supercluster, we designed and developed and tested a new autonomous launch and recovery system. Our involvement was very much key to the growth of the company, and it allowed us to take a project that we had probably on our 5 to 6 year development roadmap. Through the Ocean Supercluster, we're able to take that and condense it into a 36-month timeline. And since that time, we have grown our company in Newfoundland and Nova Scotia by 42 employees. We have partners from multiple industries and sectors that we probably wouldn't have also been able to avail of without the initiative of the Ocean Supercluster. But as well too, it's allowing us to really ramp up the development scale of it. We had a couple of announcements in the last few weeks with regards to 2 significant commercial contracts that we landed, one with the Danish Navy and one with the Polish Navy. Through that project, we're going to deliver full mine hunting systems. So that was a process that we started over 2 years ago. We got down to a final 4. The other 3 companies that we're competing with are large defense contractors in the US and in Europe, and a lot bigger than us, have more cash, more employees, but we beat them. And we beat them with our technology. We need to continue to invest in oceans. We need to stay focused on that. So I think it's really key for governments to look at that, the complete chain, right from concept to development to testing to commercialization. It's really important that we don't sit back and wait, but we put the pedal to the metal and try and drive it as much as we can. I think the opportunities are there. We just need to chase after them.
Later in the mid-80s with a couple of experimental systems, but it's not until in recent years that commercial systems have started becoming available. And the concept of SAS and SAR is kind of illustrated here. You travel along a path, here with a sonar because it's SAS, and instead of using, well, you only have a limited physical size of your array, but you use the motion of the platform to synthesize a really long array, and that enables you to get really high resolution. So before I can explain SAS, let me just review briefly sort of conventional side scan and sector scan sonars that may be used for imaging and their limitation, because that motivates SAS. So here I've tried to illustrate a sonar. Typically a SAS will be mounted on an AUV or some kind of towed platform, but usually you want to be near the seafloor when you're imaging, so it's often on an AUV. So the AUV travels along a path here, I call this the range axis, or the cross-track axis, some people call it. And you transmit pings. And each ping then becomes a line, and you put these lines together in the end to form a two-dimensional image. And you're probably all familiar with side scan.
No.
But there are some
we're not.
basic
I'm not
limitations,
familiar with that.
if you can call it that. And first, if we look at the resolution, the resolution is basically given by the beam angle. So here it's this angle here. And just looking at one of those, the opening angle here, beta, is roughly equal to the wavelength divided by the aperture size, d. And that gives you your azimuth or angular resolution. So, range and azimuth. I won't worry much about the range resolution because that doesn't change for synthetic aperture sonar or conventional sonar. It's the same.
What are
It's
these
either
formulas?
the length of your
What does that
pulse,
mean?
or usually in a SAS you will use a broadband system and transmit a chirp and then match filtering on reception, and you get a range resolution that is C, speed of sound, divided by 2 times the bandwidth. But more interesting is the azimuth or angular resolution. And in a side scan sonar, it's given by the range, well, roughly by the range or the distance from the sonar to your imaging object pixel, multiplied by your opening angle. And as we can see, of course, it gets worse with range. So the resolution degrades with range. That's something we really don't want. The resolution depends on the aperture or the receiver. I'll use those words interchangeably. Aperture, receiver, antenna, often used in radar. It's dependent on
like
the
how she's
aperture size.
translating now.
So the bigger the better, but it's often very impractical to have a
So
huge
I don't need to know the
receiver
math.
array,
She's just
especially
telling
on
us
an
the
AUV.
answers. Good.
The resolution depends on frequency because you have the wavelength here. For a higher frequency, you get a shorter wavelength, and you get a narrower beam, better resolution. So, for better resolution, you either have to increase your frequency, which isn't always a good idea because that again limits your range because higher frequencies are attenuated more quickly in the ocean. Or you can increase the aperture size. And that's what we'll do with the synthetic aperture sonar. Just briefly show you, if you didn't, or you can also have a sector scan sonar. And I'm introducing that because synthetic aperture sonar in a way is a combination of side scan and sector scan sonar. So for each ping here, you can do